Hello everyone, my name is Suchanksh and my teammate is Shashank. Today we are going to explain about the sparse matrix in data structure. Let's see the introduction part related to the sparse matrix. As we all know that the matrices are those which organize the data into rows and columns. Similar to that, sparse matrices are the special type with majority of elements being zero. In the sense compared to other matrices, the sparse matrices are those which contains the values means zero values has more elements. They are used to efficiently store and manipulate the large data sets with many zero values. And these sparse matrices are common in various fields like scientific computing, image processing, and graph algorithms. And these sparse matrices are utilized for tasks like network analysis, finite element analysis, and solving linear equations. Okay, now let's see what actually means the sparse matrix is. Sparse matrices have significantly high ratio of the zero elements to non-zero elements. As I said that the values number of elements of the non-zeros are lesser than that of the zeros elements in the sparse matrix, and they are characterized by sparsity, indicating the proportion of zero elements. Opposite to that of the sparse matrix is dense matrix, where most elements are non-zero. As the sparse matrix contains more zero elements, in the dense matrix the elements are more non-zero elements. Sparsity can vary greatly depending on the nature of the data being represented, and sparse matrices offer advantages in terms of memory efficiency and computational speed. As compared to any other matrices, the sparse matrices have the higher advantages in terms of memory and speed. Okay, now let's see how to identify the sparse matrix. In order to know whether the given matrix is sparse or not, first count the total number of the elements in the matrix. Then count the number of the zero elements in the same matrix. If the count of the zero element is more than that of the non-zero element, then the matrix is considered the sparse matrix. As I said that the sparse matrix is the matrix which contains more number of the zero elements than the non-zero elements. In such way, the number of the if the elements are zero elements are more than that of the non-zero element, then the matrix is likely sparse matrix. The sparsity of the matrix is often expressed as the percentage of zero elements, and different thresholds can be used to classify a matrix as sparse based on its application. Let's consider the example which has been given in the picture. In that matrix, it total consists of the 20 elements. Among the 20 elements, the 14 elements are 0 and the rest 6 elements are only non-zero elements. Since the number of the 0 elements are more than that of the number of the non-zero elements, this matrix is considered as the sparse matrix. Okay, now let's see the advantages of the sparse matrices. The main advantage of the sparse matrix is that it reduces the memory usage. Since the sparse matrix consists of the many elements as zero elements, the memory usage to store the non-zero elements are very less, and it is faster computational operations like matrix multiplication. As the zero elements does not need to be processed, the operations like multiplication are very easy and faster in sparse matrix than any other matrices, and efficient storage and manipulation of the large data sets with many zero entries. The another advantage of the sparse matrix is that it improved performance in algorithms that involve sparse matrices only. And the another advantage of the sparse matrix is that it enables handling of the data sets that would be impartial with the dense matrices due to memory constraints. These are all the introduction and representation part of the sparse matrices. Rest will be continued by Shashank.
Hello everyone, myself Shashank. Let's see more about the sparse matrix. Here is the representation of a sparse matrices. First is the list of lists. Let's see overview. It represents the sparse matrix as a list of rows, with each row being a list of non-zero elements. Next is here is advantages and disadvantages. First is advantages. It's simple and intuitive, easy to implement. Next is disadvantage. Inefficient for column-wise operations, potential for higher memory usage with large matrices. Next is a coordinate list. Here is the overview. It stores each non-zero element as a tuple, as a row, column or value. Next is advantages. It's a straightforward representation, efficient for construction allows random access. Next is the disadvantage. It's inefficient for row-wise or column-wise operations, may contain redundant entries. And next is compressed sparse row. When you see the overview, it uses three arrays for values, column indices and row pointers. And next is advantages. It's efficient for row-wise operations, reduced memory overhead. When you see the disadvantage, it's more complex for construction, especially for dynamically changing matrices. Next, here comes the compressed sparse column. When you see the overview, it's similar to CSR but optimized for column-wise operations. Next, when you come to advantages, it's efficient for column-wise operations and reduced memory overhead. And disadvantages are its construction complexity and may not be as efficient for row-wise operations. Next, we will see the basic sparse matrix operations. First is addition. When it comes to addition, adding two sparse matrices involves adding corresponding non-zero elements. Their zeros are ignored, exploiting sparsity. Here is the example for adding two sparse matrices. Next is multiplication. Multiplying sparse matrices involves optimized algorithms to handle non-zero entities efficiently. Next, we will see the algorithmic considerations. First is sparse matrix addition. Algorithmically, adding two sparse matrices is efficient as it only requires iterating through non-zero elements, and it's computationally advantageous due to the sparsity of the matrices. Next is sparse matrix multiplication. Efficient algorithms like compressed row or column formats are used to reduce computational complexity, and these algorithms exploit the sparsity pattern to minimize the number of operations required. Thank you.